In part 2, now that we've covered all the basic preliminaries of what is reinforcement learning all about and the very simplest case and had a look at some of the algorithms, now going to take this into the realm of deep reinforcement learning, which I guess is what most people are excited about these days. And then tomorrow I'll talk about what's actually exciting. You can all hear me okay, right? Okay, cool. Okay, so I think the important thing from yesterday is we were talking about value functions. And we were using these as a way of rolling the reward function and the transition function kind of into one, so that we can think in terms of the immediate future, right? As I said before, you can't do this normally because your rewards are typically sparse. So if you are trying to just act according to your reward function, most of the time you're going to have no signal to use to give you any information. But if you've got something like a value function which gives you this propagated estimation of how good each state or each action in each state is under a particular policy, then that gives you something that you can act greedily according to. Right? So a very useful concept for getting policies. Now, with what we spoke about before, I assumed everything was discrete. Right? So you might have like a room like this, or two rooms in two of these 25 by 25 grids, and you can think about your little agent moving around. Actually, that just reminded me of something. A friend sent me a message earlier, just completely coincidentally, about getting a Roomba to learn to drive around a space and clean it by itself, that someone was rigging up with reinforcement learning. And they decided the good thing to do would be to penalize it for bumping into an obstacle, because it's got these like kind of collision detectors in the front. So apparently the thing just learned to drive backwards. All right, so anyway. This is a discrete value function, and a discrete state space. So if you think about the value function, you might in general get some sort of shape that looks like this. This is taking each action into account. That's why it's a little bit bigger. But you can imagine something like this. You've got the kind of goal, which is over here. So that gives you the value with the highest state. And as you move away from that, there's some decaying of value. And effectively, just acting greedily according to this just says we're going to climb the hill. And that gives us our policy. All right. Now, the problem is obviously, and actually I've had quite a few conversations with several people over the last day or so, the real world doesn't look like this, obviously, right? Things that we care about tend to not be discrete. If you're doing something like a self-driving car, you could imagine that something you care about might be your GPS coordinates. It might be what's coming in through a camera. In that case, yeah, okay, it's still discrete, but it's a huge space. Or you might have like a robot, and you're trying to get it to learn to do tasks around the house or in a workshop, and there, for each arm, you might have something like 7 degrees of freedom, so 7 joints it can activate. And each of those you typically think about as being continuous. Right? And you might look at the state space as being like the joint positions, but also the joint velocities, accelerations. You might look at various forces. And when you combine that with your vision and other sensors, you're going to end up with these really large, usually continuous spaces. Okay, so this is a problem, right? Because with everything I was talking about yesterday, you're going to do kind of as I alluded to in this first picture here, you have like a table of numbers. Like for each state, I can have the value of that state and update this every time I get some experience. All right? But the second you've got real valued states or action spaces, you then also need real valued policies. You need real valued value functions and models. We haven't spoken about models yet, but you'll need those too. So this is obviously something you can't just represent like in a tabular form. Right? So we're going to move from this paradigm here where you've got this nice discrete table to some continuous function. And the problem is in making this change that a few different things happen. Right? And your big problem is firstly, okay, obviously tables are hard to store when they're infinitely large, but like what we're really doing here is we're trying to visit these states or effectively try actions in different states a number of times, and then use that to build up an estimate of value. Right? And if you think about this, I can't just do that once. Right? So if I'm in a particular state over here and take a certain action, right, I only get a good estimate of that value once I've rolled out into the future from there. So if I've got a policy to try and leave this room and I take a step in one direction, Like I only get a good estimate of that value after numerous rollouts of trajectories from that point. Okay, so I would only know accurately what the value is if I've made it to the door several times, right, to account for all the bad estimates I got along the way. But if I've got a continuous space, then like with all, the likelihood of me actually these states repeatedly is probably zero. Well, depends what you're doing. And so that's a huge problem, right? Because now I might want to know the value of a state to act under a policy if I've never encountered that state before, right? And so effectively I'm trying to generalize to actions I've never taken before from states I've never been in before so that I can estimate this value or the policy. Okay, now this has been a problem before deep learning was a thing. And people have long worried about this in reinforcement learning. And the big thing to do is to change representations. So this is what I've basically been doing in the examples I've shown you already. So you might have like a room like this, and you could just discretize this into some grid. So you could decide, all right, I want to represent this as like a 10 by 10 grid, and I'm just going to approximate everything as being under one of these cells. And in practice, for these navigation type problems, this tends to work quite well. And for kind of most of the history of reinforcement learning, these are the domains you'd see in papers. We'd call these grid worlds, and reviewers would always say you should stop using grid worlds, and then they'd carry on using grid worlds because they're nice and easy to use. But effectively, this kind of discretization everybody's familiar with. And you can get obviously more sophisticated. So a common scheme people use is called tile coding, where what you do is you have multiple discretizations over the space, and then you can just say like which cell I'm in at each layer of these discretizations, right? So I can have like tiling 1 and say I'm in this cell in tiling 1 and then this cell in tiling 2, and that defines like a more refined space, right? So it's very simple, same kind of idea. Effectively, you've just got a higher resolution grid. And then people have done all sorts of weird and wonderful things that honestly in most cases look like more work than they're worth. But there's no reason to use any particular discretization, right? So if you remember back to all the methods we spoke about yesterday, when you're thinking about your Markov decision process, all you need is a set of states, a set of actions, and the transition functions between these. So you could effectively think of any of these as like a graph, where each one of these little pieces of this subdivision is a state, and there's actions that connect neighboring states. So you can think of this graph defined over this. It's a discrete entity. We can do all this stuff we spoke about yesterday. Okay, but that's obviously well and good and not good enough to solve anything interesting, because you can imagine if you're, say, working with a robotic arm, it's not clear like how you'd want to discretize that space, right? You might do like a uniform coding like this, but that's not necessarily useful, right? You might be more likely to get more interesting stuff happening in like the region of where your joint is quite closed rather than open, and so you might want something non-uniform or more complicated than that. So the general solution to this problem is to use function approximation, right, which everybody does all over machine learning. So we're just going to import toolboxes from there. And the big thing to think about is if there's a function that you care about, and in this case it's continuous, so we want to do something that lets us compute over it, we're just going to represent it in a parameterized form. Okay, so we could have some function of our state that's also parameterized by some vector, w. And we can then write an objective function in terms of w. And this should look very familiar to everybody. Because if we just want to learn the values of w, we can just do some optimization here and like gradient descent and our normal toolbox. Okay, so this is our standard go-to tool for everything when we're dealing with functions that are hard to work with. Now, the question is, what are we approximating here? Now, it should be obvious that the kinds of entities that we care about would be value functions, policies, or models. Right? These are all the things that are capturing the information that we need about the world to actually act in the world. Right? And to some extent, these can all be thought of equivalently. But I'll go through each one of these in detail and talk a little bit about what approximation means in each case, kind of in less detail each time. Okay, so seeing as though we've put a lot of effort into thinking about value functions, let's start there. Now, before we had our value function as in the case of a Q function as a function of state and action. So what we're going to do here is include some parameters. All right, and again, this is going to be a mapping from some high dimensional space of your states, actions, and parameters to just some scalar value that gives you this desirability of this action in that state under your policy. Now, to define an objective function here, remember we're looking at these Sasa tuples, which is your experience, right? So you're moving from states with actions to future states and getting some reward. And when you're trying to learn in this case, you can just represent this as the sum squared TD error, right? So if you have a look at this, you've got this functional form that we had last time where you've got the current, your current estimates, which is the reward I get now, as well as my estimate of what's going to happen in my rollout into the future. And the difference between that and my current estimate of the value of the state and action that I'm in at the moment. Right, so what I want to do in this case while I'm learning is I also want to learn these parameters that minimize this error. Okay, so we can set this up as a quadratic error in this case. And what's this doing? Okay. All right, so if you can set up your problem in this way, then all we have to do is function approximator, compute gradients, and descend that. Right, so what we're looking at here is we want to learn these parameters of these functions and do so in a way that actually models this value function that we care about. So I've just described this in this general form, some parameterized function. So what's the simplest thing you can do here? You can just do like a linear value function approximation. And kind of as Neil and everyone else has been talking about, this is always a good obvious first step. So what you can do is define a set of basis functions and then define your value function as a linear combination of these things. Right? So you might have your approximate Q value function, we've got the approximation with the hat, as just this weighted combination of these potentially nonlinear basis functions. And so obviously this should be ringing bells from like half an hour ago, that there's all these other toolboxes you can import into these settings. Okay, now for function approximation, with that being the functional form we have, you've got choices of like what kind of basis functions you want to use. And the choices you make there are going to affect what happens with learning. Right? So obviously the trivially easy thing to do is just use your state variables directly. Right? So if you care about variables x and y, then you just have some linear combination of x and y, and we'll add a bias because that's usually the good thing to do there. But that's obviously not adding any interesting representational power to your problem. Okay, so the common things then to do would be to go to like polynomials in your state variables, and you can take this to like whatever arbitrary order you want. And effectively then all you're doing is like a Taylor expansion. Right, so and if you have enough of these terms, you can approximate whatever continuous function you want to arbitrary accuracy. But then all you have to do is learn a parameter that goes with each one of these features. So effectively what we're doing here is we're taking like our state space representation of the problem, which is in x and y, and we're just making some assumptions about the structural form that we think is important for this. So we're saying we think these features like y squared x, for example, are also important for modeling what we care about in the space. And obviously the value of doing that is we can just think linearly about these basis functions here. All good so far? Cool. And then there's all sorts of other exciting things you can do, and there was a whole game in reinforcement learning for a number of years. If you came up with like a cool set of basis functions and you could show that worked on certain problems, you get to write papers about it. Right, so you can decide, all right, the Fourier series is a great thing to do. We can just use Fourier series approximations of our functions and do the exact same thing. Have like a parameter associated with each one of these terms, and then just learn that in the standard setting. Okay, so talking of learning, we're going to do this with gradient descent or stochastic gradient descent. and then just treat it as follows. So as each data point comes in, now just a quick recap. Remember, in the reinforcement learning setting, when we're taking like our batches of data or individual data points, it's not like in the supervised learning setting where you're just drawing from a data set. Here what we're doing is actually acting in the world. So we're gathering our data from our own interactions with the environment. Right? We'll pick some action through some exploration scheme or from some policy, and that's going to give us our next data point. Right? And when you get that, you can descend the gradient. Right? So you can just minimize your objective function, where your basis functions come in here as before, and again, this is of the form of the TD error. Any questions? Okay, so this is really not among the most complex maths we've seen today, but if you want to work out what the contribution is for each weight, you just want to take the derivative of this error function. Now, typically what happens, and I'll talk a little bit about this further, is we're going to, when we take this derivative, we're going to assume that the weight on this second term here is fixed. Now, this is the target, the TD target that we spoke about yesterday. And this is, if you remember, like our estimate of the value at the current point. So what we're saying here is we're looking at the immediate reward and the estimate of the value of that state going forward. That's where I would have ended up when I take this step. And we're going to treat that as fixed. And there's convergence reasons to do this, which for these kinds of basis functions isn't a huge problem. It simplifies the maths at this point. But like later on when we're using neural networks, that's going to be very important for convergence. So we treat that estimate as fixed, and the weights that we're treating as variable are the ones on like our current estimate of the state and action we're currently in. Okay, so if we do this derivative and we're looking over a set of data points, then for each state we can write out the contribution here to the change. So for each state Si, the change to weight Wj we can write out as this term here. And again, there's the TD error, which I did warn you would pop up all over the place. And so once you've computed this, you can just make a step in that direction. Right? So I've got the effect of this state, at this iteration on this weight, I can update it according to this error by taking a step alpha in that direction. And it's often just written in a condensed form like this, where this little delta represents the TD error. Right, so this is just your standard gradient descent update. We're going to take our weight, take a small step in this direction, and this is the direction that gives us this contribution here, which says we're looking at minimizing this discrepancy between the current estimate of the value function and the revised update having received reward Ri. Okay, all happy with that? My laptop's being really confused about what my next slide is. It looks like my last slide. Okay, so this has been like commonly used in reinforcement learning for quite a while. So for example, we can look at like a simple toy example, which is often not treated as a toy example, called Acrobot. So here what we've got is effectively a double inverted pendulum, and you want to swing this thing to try and get it to stand upright. So so you can look at several episodes of learning here. Now remember, this wouldn't have been possible if you're just looking at the discrete description, because your state space here is like you could take your two angles. So you've got the angles at the two articulation points and the velocities at those 2 points. So you can take those four dimensions, and they're continuous, obviously. Now, if I was going to be discretizing these things, it's very likely that that wouldn't give me the kind of refined level of control that would be able to describe the policy that I care about. So what you can see here is like the first episode is quite a long one. It's going to just keep going until it actually gets the endpoint over the red line. This was longer than I remembered. Okay, so it achieved that. So that was the first time it got some positive reward. Okay, so that whole time it was just taking random actions and not learning anything. It's only when it reached the endpoint that gave it some information that it could use to propagate back to learn something about the problem. So you can see there the second episode was somewhat quicker because it's not acting completely blind anymore, right? It's getting very sparse signals. It's doing a lot of work to get a little bit of feedback. It's playing its whole game of chess over here, and then gets this tiny bit of information and says, okay, next time try and optimize to receive that again. All right, so it's doing a lot of exploration in the space, and that's more a feature of the sparsity of the reward function. So if I remember, this should be getting better by now. Okay, so you get the gist of this, right? It slowly gets better and better, and eventually it should be pretty good at doing this. But it's got to do quite a lot of exploration in these continuous spaces to learn this. Now this was done using the Fourier basis. Okay, so let's stop at 6. This was done using the Fourier basis. And so you can look at the kinds of learning curves you would have here. Is the number of decision points that it has to, or decisions it has to make to be able to learn to swing this up. And you can see in the first few episodes, this might take like thousands of decision points to figure this out. Because bearing in mind, it doesn't actually know anything about the problem at that point, right? You've just like gone to a baby and given it a joystick with a few buttons and said, do stuff. And then eventually you walked in an hour late and said, well done. Like that's the experience of the learning agent in this case. And the kinds of curves you'll tend to see would be using different choices of basis functions here. And you can look at like how this affects the convergence. All right, so this makes a big difference in how you're learning, is your choice of basis functions. But this does let you deal with these continuous spaces. Now, the fact that we're using this this particular form where we're writing our value functions as this linear combination of weights and basis features means we can do things like think about least squares, right? So if we've got a whole batch of data, now imagine we've sat there and been collecting data from different parts of the state space. We could take a whole batch of data, and because of the structure of the error function, there'd be a unique minimum, right? So if we've got this convex function and enough data, we should be able to just optimize it directly. And this is what's called least squares TD, right? So this is a reasonably straightforward method where you can just rearrange your terms and solve for W, right? And then obviously you can do all sorts of things with your pseudo inverses and things, but I think this is useful to think about the problem as we've got all these data points that we can collect, and we can use these to kind of solve in all these different ways for these sets of weights. Now, in practice, this is not what people do very much because we've made a lot of simplifying assumptions here, but just to give you an idea of the structural form of what's going on here. Okay, so, I mean, everybody in this room is familiar with this idea of just picking basis functions and optimizing things with that. But, so, it should be no surprise to anybody that linear methods don't scale. Okay, and oh no, this is like such a shock because we didn't see this coming because they've got all these nice properties of convex error surfaces and easy to compute with and all these kind of things. But the really big problem that was always a limitation in reinforcement learning is the number of basis functions that you need to express your Taylor expansion to like an arbitrary degree of precision, right? So this just grows exponentially in your number of variables, right? So as I showed with that earlier example, you can go to arbitrary orders of your polynomials, and if you've got, say, 10 or 100 or 1,000 state variables, then that's completely not feasible, right? So as I said, no surprises there, but just to give you the intuition of how we're going to deal with these continuous spaces. So I think the kind of big exciting breakthrough in this area came in the early 90s, where Jerry Tesoro came up with what was called at the time TD Gammon. And this was considered one of the first big breakthroughs of reinforcement learning. And that was in getting a TD learning agent to play the game of backgammon, right? So at this point, this is very much a solved problem, but back then it was a pretty big deal. So you'd have something like 10 to the 20 board configurations as your state space. You've got all the actions of moving these pieces around according to the rules of the game. And you can set it up using just the standard rewards I've been talking about all along. You get like a reward of 1 for winning, -1 for losing, and 0 for drawing. So you play a whole game, you see what happens at the end of it, and you learn based on that signal. And the neat thing that happened here was this model used a neural network function approximator to learn the representation of the value function. So it was a very simple model. There were just a couple layers in the network. But this was quite a big deal. This is a reasonably complicated problem with a reasonably complicated state space. And turned out you didn't have to be that selective about your basis functions. You could use something like a neural network to learn this as to the precision required. And that ended up beating human level play. And even subsequently, people now play according to rules that have come out of this and successor models. So this was like a super big deal in the field. But it took a while for this to really take off. This took the whole deep learning revolution that affected everyone else to be really taken seriously, which is quite interesting because this was already quite a big success a number of years before this started happening in other domains. So this kind of gives the clue that this is what we're really looking for. Now, anyone who's spent more than 10 seconds looking at reinforcement learning in recent years will know that this is one of those hot domains. This is called the arcade learning environment, where there's a whole number of different of these old Atari games that have been emulated, and you can now plug your reinforcement learning agents into this. But this has all these properties that make it so difficult, right? So you've got, in various games, you're dealing with, so take a step back. What you've got here is you've got the pixel array that comes out of each frame of this game. And now you're trying to take actions which correspond to like pushing joystick buttons or arrows or something to control whatever it is that needs to be controlled in each particular game, while all you're receiving is the pixel array from the screen. Now this will depend on a game-by-game basis what each one is doing and what you're controlling and what's important to pay attention to. But it's clear that you couldn't do this with just a standard tabular model, right? And picking your basis functions for something like this, although I've got colleagues that are convinced you can do everything that you can do with neural networks with stuff that's much simpler, it's a bit of a pain to think about the basis functions that you want to choose in each case. All right, so this is very cool. Anyone working with RL, if you haven't played with this before, you should. You can just easily plug in models. And the very neat thing here is there's dozens of different games now that you can just connect your agent to. So this inspires a whole way of thinking, which I'll talk about more tomorrow, where you don't want to encode a lot of domain-specific information. You'd like to be able to unplug your learner from Breakout and plug it into Pong and have it learn in that case as well. And that, again, is one of the beauty of using something like a neural network to approximate your value functions, because you can do this in a general way. For games that have particular structure or size of the screen, you'd imagine that maybe the same network is sufficient for that. And turns out, in many cases, it is. So I'm going to talk about one specific model that people use in this case. Now, if you remember yesterday going through all these different algorithms, we ended up with Q-learning. So that was when we were taking actions into account, as well as states, when we were learning value functions, and we also wanted to do it off policy. So the extension to this in the deep learning sense is called a deep Q network. Right? So the basic idea here is, again, we're going to be trying to learn the Q value function. And this is one of the papers that received much excitement, that launched DeepMind into becoming an international hit phenomenon. So effectively what is going to happen here is you're going to take your data, and you're going to learn a neural network on top of this that ends up predicting the values of different actions on this. Right? So you can think of this as you've got an input state. We've got a number of layers of a network, which convolution and fully connected layers. And at the end, we're going to have spit out some values for the value of these actions in that state. All right, and that actually ticks the boxes of everything we've been talking about. We want to be able to make predictions about the value of states that we may not have visited before. And that's kind of built implicitly into all these assumptions of the neural network, right? So we're using things like convolution to say we expect that values are going to be similar in adjacent or very similar states in the network. And we're going to leverage all that theory to be able to learn these value functions. So let's have a look at the DQN. So just to look at this algorithmically, what you're going to do is, in the same kind of way we've spoken about doing before, you need in a loop to be able to take actions according to some policy. You can do something like epsilon greedy. And you're going to store this transition, right? So this is slightly different to what we did before. And we'll discuss that. But what you did before is you took each sample, you learned with that sample, you discarded that sample. And here what we're going to do is keep it in this replay memory. You're going to take that replay memory and draw some samples from that. So you're going to take a mini batch out of the memory. And the important thing here is that, well, this way of acting is called experience replay. So I'm going to store everything that I've encountered in the past before. And when I draw these samples, it's actually serving to decorrelate them. Now, there was the minor rant about independent data earlier. But effectively, if you think about it, if you're trying to learn from IID data in general for your neural network, that's exactly what you don't have in this case, right? So I'm busy executing some trajectory as I move through the space of this game that I'm trying to play. But like every single state and every single action are all correlated, right? So you could think if you're exploring a room and you're just mucking around in a corner, it's not like the data is independent, right? You had to get there some way. You tend to not be teleporting as you're moving around this domain. And so there's these strong correlations that you want to break. So if you store everything you've ever seen before in this replay memory, and you just draw random samples out of that, that's a way of breaking these correlations. And it turns out you need this for these methods to converge. Then what you want to do is you want to compute these Q-learning targets. And as I was saying, you want to do this with respect to the old fixed parameters. So we're going to treat this, so we're going to treat the, if I went back to the previous expression of the cost function here, we're going to treat the ones that's looking into the future as being fixed weights. And this, again, has important implications for convergence. If you don't do this, you end up getting oscillations. So your values of your Q network and the weights are going to oscillate. And you're going to end up not converging in this case either. All right, so then we're actually just, once we've done this with these two tricks that we've had to throw in here, we can then treat it as we would expect to, right? So we're going to take this mean squared error between our current estimate and the updated estimate, and we're just going to optimize this using stochastic gradient descent. Okay, bearing in mind that we're going to keep our samples as drawn from our replay memory and keeping these weights here fixed. Okay, so that's the gist of the DQN, and I hope again that I'm getting across this idea that there's a lot of common structure to these algorithms. But this is really what it took to learn to play 50 different Atari games, right? So these slight variations on the same Q-learning that we spoke about yesterday. So this is end-to-end learning of your value function, right? So we're working with pixels, although to get this to work, another trick that was used was to not use a single frame, but to take a stack of 4 frames, because effectively that gives you an approximation to like your velocities and accelerations of the frames, which makes the thing a lot easier to learn if you know what's moving. So you would take 4 of these frames and effectively plug them through this network, and then your outputs would just be values of the different actions depending on how many actions were in that game. So that was one parameter that you need to change. Different old Atari games have different numbers of actions you might execute. And then the reward is just your change in score for that step. Right, so a video that I'm sure everybody's seen, but just in case, here's from 2 Minute Papers, a video of this algorithm learning to play Atari Breakout. So again, the important thing is that this doesn't have any domain knowledge, right? So it gets the pixels, it knows what actions are required, but that's all you're really told about the domain. So the nice thing is, with something like reinforcement learning, you can act however stupidly you want here and something will still happen. So when you start training, you can just take random actions And sometimes you're lucky and something good will happen, but most of the time you miss the ball and end up losing. So in each of these cases, especially at the beginning, it's acting randomly, and it's collecting this data as it learns, and that's getting plugged into this replay memory. So after about 120 minutes of game time, once you've collected a considerable amount of data and you've done a lot of updating of these value functions, again represented as a neural network, now this thing's actually learned to play. All right, which is actually pretty quick in terms of the amount of gameplay. And then the super cool thing is if you just keep optimizing, then you start discovering all the hacks in these games that anyone who might have played this as a kid figured out. Right, so it turns out the best way to play this game is, contrary to not thinking about it much, if you dig a tunnel through the side, you get a lot of points very easily. Right? So this is very cool, right? So you can see similar results in a whole lot of different games using the same network architecture, not the same network. And you probably can't see from there, but these were some of the original results. These are all kind of improved considerably since then. But what you can see here is these are the number of games that were played here, with this line indicating above human level performance. So they had some people playing these games in the labs for benchmarking. And you can see for a bulk of games they outperformed humans. And the DQN, in most cases, you can see the relative performance between the DQN and the best linear learners. And you can see in a number of these games they're considerably better than human level play. All right, any questions at this point? Yeah. Sorry, what do I think about? Gaussian processes. Okay, so there has been a fair bit of work like that. I think it's very cool. It's been particularly successful in model learning, and that's actually Mark Diesenroth's done a lot of really cool work there with the model Pulco. And the nice thing with the Gaussian process is if you can make some assumptions about what you expect to happen, for example, in the dynamics of the domain, it's very easy to learn. You need very few samples to actually learn, and this turns out to be very useful in fairly complicated processes where you've got, say, robots trying to act. We did a paper recently where it gives you a very nice way to incorporate constraints into your problem. So definitely, if you can use Gaussian processes for the problem, I recommend it. Anything else? Okay. So the next piece I want to talk about is doing function approximation with your policy rather than the value function. Now, this is a different class of algorithm called policy search algorithms that operate directly in the space of policies. And the idea here is that in many cases, it's easier to think about policies directly without worrying about the value function. So one example might be trying to pick something up with a robotic arm, right? If I were to model the whole state space, if I've got a lot of other things I'm taking into consideration, like that could be quite a complicated value function in a very high dimensional space. But the policy might be able to be described very easily in terms of like the relationship between the end effector hand position and the object you're trying to pick up. So in many cases, you can actually describe your policy quite concisely without worrying about the goodness of states. So in this case, we're here going to parameterize the policy. In this literature, we tend to call this parameter theta. That's not my inconsistency. And so what you want to do is, if you remember, your policy is just a mapping from states to actions. And if it's parameterized, we just want to learn the parameters of this policy. And I've said that. Okay, so what we're going to try and do is maximize the reward given these parameters. So find the setting of the parameters that give you the best reward with your policy. So there's different settings. You can't always differentiate your policy, and this depends on how it's set up. So In some cases, you might need other ways around this. And here what you'll do is just approximate the gradient. So you can sample values of the parameters in the neighborhood of your current policy, and then just keep adjusting these things. So I think a really nice example here was there's this competition called RoboCup. I don't know if anyone's familiar with this, where it's been going for, I think, about 20 years now. And every year there's this competition where a number of teams enter and have a team of robot football players with the goal of, by 2050, beating the human world champions. And it gets slightly more realistic every year. But there's this league called the Standard Platform League, where everybody has the same robots, so hardware isn't the thing. It's about the logic that you build into this. So for a number of years, it's not the case anymore. People were using these IBOs, which are these little robot dogs, because the control was easier than using humanoids. So up until this point, hang on, I have to turn this off. Okay, so this was kind of the standard policy that people would use for navigating or for locomotion with this IBO. You can see it's not exactly useful for doing anything. Right, so they define the policy in terms of a number of these parameters of the leg. And this is how people would typically play these games. So you'd have a bunch of drunk robotic dogs chasing a ball around a field. And then using this policy optimization back in 2004, you could get something that's quite a lot cleaner and more elegant and faster. And now this kind of thing's been repeated. Now these leagues use humanoid robots, and they use very similar kinds of procedures to optimize the gates for these things. Where before they were hand-tuned by like huge teams of undergraduates. They would spend all their time tweaking parameters and trying to figure out the best way to get these dogs to move. Right, but that's actually not the most common case. Generally, you can differentiate your policy, and then you can just, again, do some gradient descent and to try and get to maximize this, the reward given these parameters. So this has actually been spoken about a fair bit over the last couple of days. Like, for example, Shakir was talking about it. And this method's called reinforce. So this is like the simplest thing you can do in this space. There's now a whole zoo of these different methods. And it's a sample-based estimate of your gradient. And effectively, you're just going to update your parameters based on the this reward function and this derivative, which turns out under the log derivative trick that Shakir was talking about, so I had to include it here, to have this nice, clean, functional form. Right? So you're going to, as you collect samples moving around the environment, you're going to get updates of your return. So the capital R here is your return, so that's the reward accumulated over the whole trajectory. And you're just going to update these parameters in this way. So this gives you a very, very simple algorithm that says we're going to choose our actions according to our current instantiation of the policy. We're going to record these samples, and then we can traverse through that trajectory and update the parameters of this of the policy, update the policy parameters based on the rewards received and the derivative of the log of the policy. Right, and effectively what that's doing is that's saying we're going to adjust the parameters of the policy in the direction of improving the reward. So if you're getting a positive reward here, you're going to increase these values and effectively decrease them if you're getting a negative reward. And then, yeah, there was the discussion also before about the variance of this. So what's not great about this method, as I say, there's a whole lot of these policy search methods. This is the simplest one. But what you tend to do, you tend to have problems with the variance of this method. So it's unbiased, but it has high variance. And so in practice, you subtract this baseline term, which, if anyone cares, tends to be equivalent to the value function. And actually, using different ways of dealing with this variance here gives you a whole host of other methods. So you can derive actor-critic methods from different ways of looking at this baseline and correcting for this variance. But the basic idea is what you want to do is you want to take this policy and, as I say, as this is gaining your experience in your domain, you want to be able to tune these parameters to improve the performance. Now, this has been particularly successful in robotics lately. What's called deep policy search, and there's, again, a variety of these. So there's some really cool work that's come out of Sergey Levine's group, where they've been getting this two-armed robot, the PR2, and getting it to learn to do a whole lot of different manipulation tasks. And the basic idea works something like this. You can represent your policy as a network like this, where you're taking as input your RGB image, you're taking as input as well, like the robot configuration. So you've got 39 joints over there, and passing through a number of conv layers, you can end up getting your motor torques. Your motor torques being the forces you're exerting at each motor. So in this case, for the single arm, there's 7 motors that you want to activate, and effectively here we've just got a representation of a policy, right? So this is taking as input a state in action and producing like your distribution of the actions of what you should be doing. Oh no, sorry. You're taking your state in both the arm and the camera, and you're producing your actions coming out of that. And this can be used to learn to do to solve a whole lot of different problems. There's a bit more that goes into this. So effectively, they had to do a lot of additional training in this case to learn particularly the visual components. So when you're working with robots, if anyone's done that, like doing anything deep learning based is really difficult because you don't want to collect data. Or if you're acting in a reinforcement learning setting where you've got this huge state space coming from your camera, you don't want to just act randomly through exploration when you've got like $1 million robot. That's generally a terrible idea. And so there's a lot of like offline training that goes into this, particularly to learn things like pose models of the objects and the configurations of the robot before you actually start generating trajectories. So a lot of these methods, what they actually do is they augment this policy search with this initial phase where they'll have effectively demonstrations that are given by hand-coded controllers to give you some extra data. And if you remember, the whole idea of Q-learning is that you can learn off policy. So if I've generated data from somewhere else, I can use that to augment my data space, and I can still learn from that. So I just wanted to include a bit of a video to demonstrate that specific work, because I think it's rather cool. It says with audio, so I should add audio.
We present a method for end-to-end training of deep visuomotor policies that map camera images and robot configuration directly to motor torques. Our convolutional neural network policy has 7 layers and 92,000 parameters. We vary the position of the target in each task, perform insertions with only 1 millimeter of tolerance, use a variety of different grasps that must be determined from images, and screw bottle caps onto bottles. Here, the policy must determine the distance to the rack from monocular images to successfully place the hanger. The policy generalizes to racks with clothes, without additional training, as well as small objects on the hanger such as towels. Here, the robot inserts a block into a shape-sorting cube. The policy was trained with the cube in the robot's arm, but generalizes to the cube sitting on a table. The hammer task is performed with various grasps, which the robot must identify by watching the toy hammer and its own gripper. The policy generalizes to placing the hammer under the nail in the presence of clutter. The bottle task requires screwing the cap onto the bottle. This visuomotor policy also generalizes to the presence of clutter in various positions.
All right, so I think the important thing to pay attention to here is obviously that, this is a really rich space. The visual space, the configurations of the robot, and this has got some pretty impressive generalization capabilities. Well, at least from what's been shown here, right? If you change anything up too much, it obviously can't generalize beyond what it's seen in the data. But that's really impressive, right? So it's learned these policies directly from experience with the world and been able to generalize these different settings. Yeah, question? Oh, okay. Any other questions? Not that there was a question. Yeah. Okay. All right. So the way to think about this is you can use these neural network-based methods to do things like approximate your value functions, from which you can derive your policy, or to learn your policies directly. And then there's the third way of doing things. So I have not spoken much about models at all. That's going to be one of the focuses of the talk tomorrow. But what you're doing in model-based reinforcement learning effectively is you want to try and learn a model of the transition dynamics. There's been a lot of work in this recently. This is currently a very hot topic. But what you want to do here is you want to learn essentially the physics of your domain. So if I know I'm in a state and I take a particular action, where am I going to end up? Either as a state or a distribution over states. Right? So if you remember back to the beginning of yesterday's talk, if you know these things, you can then effectively run mental simulations of how the world is going to evolve when you've taken different courses of actions. And you can compute this just through something like value iteration, offline, without any experience in the world. Right? So in the ideal case, this is what you want, but the problem is we typically don't have these models. And there's been a lot of work to do this, right? So you'd like to be able to have some sort of a tree of the different ways the world could roll out. So if I try different moves in different situations, what's going to happen? Because then effectively searching the tree becomes a fairly straightforward thing to do. And this is particularly to answer the question from earlier, where Gaussian processes have been used to a great extent, but there's a lot of work using deep nets here as well, and even decision trees have worked particularly well in this case as well. Right, so particularly in cases where, in something like robotics, where you'd like to have a model of how you think things will pan out, this has a lot of advantages in terms of trying to deal with contingencies you haven't dealt with before or seen before. If you've got this reasonable model of the physics of your domain, that does give you a way to generalize beyond what you can do with the policy or value function-based methods. So just as an example of the kinds of things you might have, you could have a model like this that takes as input like a state representation, perhaps over a few frames to give you some sort of idea of the velocities, as well as like an encoding of your actions. You'd like to be able to put this all together and be able to predict observations, as in what state am I likely to see next, and reward, what do I think is going to happen here in the future. All right, so this is the kind of model that people use for these things. And actually what's quite neat is often you'll have the same neural network doing this. So you can use like a two-headed neural network because it's reasonable to assume that the features, or in many cases, that the features that are useful for predicting the next state are also going to be useful for predicting how good that state is. Right? So if you think about like what you're trying to learn here is, can I identify things that look like win conditions, lose conditions, and things when something bad might happen, and that prediction of the reward is going to be tied to the way that the dynamics evolve in the environment. So we've looked at these three different ways of approximating what could be happening in your domain using neural networks particularly, but any kind of function approximation. So yeah, just to sum up, those are the three ways you can use this, and this really gives you a handle on on dealing with problems where you've got a continuous or really large, particularly state space, but action space as well. And so that allows you to import all these tools from supervised learning, right? You get to bring all your deep learning toolboxes, your Gaussian processes, whatever you want. And then now recently there's also been a lot of work in bringing in things like attention models as well. So if you've got some complicated domain, you might want to focus on different parts of the domain. You might want to be able to use auditory signals as well. And again, all of this can just be incorporated in the same kind of ideas we've been talking about. So that's what I want to talk about today. And then tomorrow, I'll move on to talking about how to abstract behaviors. Thanks.